A very good morning to
Good
one
morning.
and all. I think it's echoing something. Others can mute yourself. A very good morning to one and all present here. It's a great pleasure for all of us to be here. I is Tamim Nisha, Assistant Professor at Dwaradas Govardhanas Vaishnav College, Chennai. I welcome everyone for this wonderful occasion of commemorating Indian Teachers Day, 71st Remembrance Day of great Indian mathematicians S.S. Pillai, and the seventh lecture of this lecture series in mathematics conducted by Pi Mathematics Association, Chennai. Pi Mathematics Association established on June 18th in 2007. This association has facilitated more than 200 lectures in various schools, colleges, and institutions, and it has conducted numerous workshops and exhibitions to popularize mathematics. And moreover, the association has published 12 books so far on maths, which have received great responses from students, teachers, and general publics. The, te- the teachers of Pi Mathematics Association have been involved in helping students who cannot afford to have private classes by taking free classes in mathematics to various organizations. This initiative has helped many students to understand the of mathematics and achieve future heights in their careers. The world is full of diamonds and gems, and we are having some of them here today to build this event. I would like to give my heartiest welcome to our chief guest, Dr. Balasubramanian, who is very famous from Chikkal to Chicago. He has held up by various postings in various institutions across the globe, such as TIFR, IAMS Chennai, Institute of Advanced Studies in Princeton, where he had a great interaction with many mathematicians, including the field medalist Adley Selberg. Professor Balasubramaniam received numerous awards for his achievements. Santi Swab Patnagar Award, B.M. Birla Award for his notable contribution to number theory. His achievements continue to till date. We welcome you, sir.
Oh, thank you. Thank you for a nice
No, sir.
invitation.
I need to, yes, sir. Thank you very much. But I need to invite some other people. Yeah, and now I want to welcome Dr. Tangaturai, scientist, Harshchandra Research Institute, Allahabad, who got the great inspiration from Dr. R. Balasubramanian, and he is also a collaborator, Balu sir. Dr. Tangaturai has published more than 60 research papers. Welcome, sir. I welcome Dr. R. Shivaraman, founder of Pi Mathematics Association and associate professor of DG Vaishnav College, who has received National Award for popularizing mathematics among uh, Masters in 2016, Indian National Science Academy Teaching Award in 2018. He also received two States Government Book Award for the years 2011 and 12. And he has provided 300 lectures and 100 research papers. We welcome you, sir. And I welcome all the dignitaries, dignitaries, celebrities, guests too for this wonderful occasion. And I especially welcome for Dr. Vijay Kumar, Dr. Yogesh, trustee of Pi Mathematics Association. Now I invite Professor Tangadurai to address the chief.
Hello.
Ah, yes, sir.
Hello. Okay.
Yes, sir, it's
Good
audible.
morning. Yeah. Good morning to all of you. On the auspicious occasion of Teachers' Day, I take this opportunity to pay my gratitude to the distinguished speaker today, Professor Balasubramanian, for the inspiration uh, to the younger generation of my time as well as now and ever to come. Among academicians, he is well known. He is called as Balu. He is well known in the name of Balu. He is a very highly accomplished mathematician, very successful academic administrator, as well as a very good inspiring teacher. Being a very good teacher, he is very accommodative and approachable person. He has written about 160 research articles in a highly reputed journal and guided as many as 13 PhD students and many postdoctoral students as well. As the previous professor said, he has received numerous nationally and internationally awards. The I mean, the latest one is Padma Shri in 2006. That is the highest honor. And also he is a fellow of all the three Indian academies, fellow of, and some of the works I would like to mention of his contribution. During his PhD days in Tata Institute, he improved the old result of Tishmarsh on mean square of Riemann-Zeta function and theorem of Hardy on the gaps between zeros of Riemann-Zeta function on the critical line. This is considered very highly, and it fetched him Young Scientist Award in 1978. Later, he has done many work. Notably, I would like to mention few of them. One is, of course, Waring's problem. He settled the 300 plus odd years old problem of Waring, along with Dejeuve and Dress in 1985. And 1995, one of the, applicable thing, along with Koblitz, his result on elliptic curves discrete log problem guaranteed that elliptic curve based cryptography is more secure than the classical one. Uh, he has been in not only in academics but also in academic administration all along. The major funding agencies for sciences like CSER or DST or NBHM, he has served in all these three and more for many years. Especially, he served as a member of NBHM for many years, and he served as a chairman for at least 2 terms, I guess. So when he was at the age of 49, he became director of Institute of Mathematical Science and continued to be director for 3 consecutive terms. During his directorship, he took over one more institute. Sets the kind of as a honorary director, and till 2020, he was the director of NCM, National Center for Mathematics, Mumbai. He gave a prestigious plenary talk in International Congress of Mathematicians at Hyderabad, 2010. His illustrated career as a mathematician is truly inspiring to any youngsters to take up mathematics as a career. I'm really grateful to him for his guidance, help in many ways on this occasion of Teachers' Day. I am thankful to the Pi Institute as well, especially Professor Shivaraman, for giving me opportunity to pay my gratitude to him. Thank you, sir. Please.
Thank you, sir, for your wonderful introduction. Now I'd like to call upon our chief guest, Dr. R. Palasubramanian, to deliver his lecture. Sir, please.
Am I audible?
Yes, sir.
Yeah. Good. Very good morning to all of you on this Teachers' Day. And Tanga gave a beautiful introduction to me. And I should only add saying that I am proud that he is one of my grand students. I am happy to talk on some good teachers of mathematics on this Teachers' Day. Teachers' Day is universally celebrated on October. In India, we do it on September to commemorate Dr. Sarvapalli Radhakrishnan, who was our vice president and so on. The teaching profession is a very noble profession. The teacher is the light of the world. the beacon in the dark. He is the hope that gives us the strength to survive. So that's a Japanese proverb which says, better than 1,000 days of diligent study is one day with a great teacher. And Dr. APJ Abdul Kalam says, teaching is a very noble profession that shapes the character, caliber, and future of an individual. If the people remember me as a good teacher, that will be the biggest honor for me. And I am now going to talk about some great mathematical teachers who have also established themselves as great number theorists, both in the last century and this century. And then if you want to talk about number theory in India, as usual, it starts with Srinivasa Ramanujan. The story of number theory in India starts with Srinivasa Ramanujan. And that is not something which I am going to talk in detail today, but mainly for the reason that all of you would have read many articles. Probably you would have read the biography also, The Man Who Knew Infinity. And also every December 22nd, you would be some documentary or something like that on the TV. And then probably there was a movie also on Srinivasa Ramanujan. And I assume you would have all seen. And even though most of you might not have understood the depth of the mathematics that he did, but at least his biography you would be knowing. Now I go back to the others. But here I have a serious problem, namely this being an offline lecture, it is not very clear to me. I mean, what is the level of the mathematics that one can assume on the part of the audience? Therefore, mainly I have made it somewhat devoid of mathematics. And therefore, my main motive will essentially be to say that number theory was not over with Ramanujan, and it was continued by many people. And in fact, most of the young audience who are probably in the college, if I ask you, can you name a couple of number theorists in India? Most of them would start with the Ramanujan, and more or less they would stop there. And probably some of them may say Shakuntala Devi, who, at least according to the mathematician, is not a mathematician at all. And that situation should change. At least the young students should know who are the number theorists in India after Ramanujan. What did they do? Yeah, unless you know your history, you cannot evolve. And therefore, the history is very important, and you should know that, and that would be my aim. My aim would be to say that there were many mathematicians, many great number theorists, probably not as great as Srinivasa Ramanujan, but still great in their own right, who are succeeding Ramanujan. And if I can introduce a few of them to you, I think I would have done my duty, and that's exactly what I plan to do. The success story of Ramanujan has stimulated many young students of mathematics from India, particularly from South, to take up number theory and excel in it. And many of them did do that. And our story starts with K. Ananda Rao. Ananda Rao had his early education in Chennai. He sailed to England in 1914 I mean, this is exactly the success story of Ramanujan. And he cleared the Cambridge typos in 1916. His earlier work was on summability, and it may be a good idea to talk about what this means, because I don't think summability is taught in the colleges nowadays, and therefore you may not even understand. But summability was at least a very important subject, a central subject at the time when we were talking about, at least particularly in England. In England, people summability was one of the central areas. But what is summability? You know what a convergence sequence is. And if there's a convergence sequence, and it has a limit and you can give a meaning to that. But there are many times when the series may not be convergent in the strict sense of Cauchy, which means that an plus 1, an plus m minus an may not be less than epsilon as n and m goes to infinity. But even then, you might be able sometimes to really get some meaning of the sequence. And you sometimes you may be able to handle the sequence. The way of doing that is what is called summability, and Harley also had a book on divergent series, which is therefore the series which are not convergent, but on the other hand, where you are able to give a meaning to the sum of the things. And as you might have known, Srinivasa Ramanujan was a great expert in it. Anyway, going back to Anand Rao, Anand Rao became a professor in 1919 in the Presidency College in Chennai. And his main work was his Riemann zeta function. Probably I should just say what is the Riemann zeta function. Riemann zeta function is an analytic function which was introduced by Riemann. And that statement is slightly wrong because even before Riemann it was considered by Euler. But Riemann is the one who mainly worked on that area. And this is the function which is somehow one sees that it contains all the information about the prime numbers. I mean, that's what we feel. And therefore, if you want to study about the prime numbers, about the sequence of prime numbers, about the distribution of prime numbers, then one has to study this Riemann zeta function. The advantage which Riemann had compared to Euler is Euler considered this function as a function of a real variable, and as such it was existing only to the right of 1. But Riemann considered this as a function of a complex variable, and some of you would have seen some complex variable know that even if you have a function defined in a certain area, then there is a process called analytic continuation, and this process enables you to look at the function in the whole complex plane, and that's exactly what Riemann did. Riemann considered this function as a complex plane and studied the analytic properties, and in fact proved the prime number theorem. The prime number theorem is a theorem which says approximately how many primes are there up to a given number n. Therefore, capital N is given, rather very large. You want to know how many primes are there up to capital N, approximately at least. And he gave a proof. But of course, there was a small gap in the proof which was finally filled up by Hadamard and Vallabhusam. And in fact, as Tanga was pointing out, this is where I started my research also. My research was also essentially on the Riemann zeta function. And particularly, Anand Rao proved a canonical factorization of s minus 1 into zeta s. And this canonical, the proof of this canonical factorization was very well appreciated by Casey. Okay, the Casey is one person who will be seeing again and again, and that is K. Chandrasekhar. And then he worked on elliptic functions also, and on Walling's problem. This Walling's problem was also mentioned by Tanga, and this Walling's problem will come again and again in this lecture, because there are many Indians who have contributed to the Walling's problem. And what is Walling's problem? Walling's problem is, given a positive integer k, does there exist an integer s such that every natural number n can be written as n is equal to x1 power k plus x2 power k plus etc. xs power k in non-negative integers xj. In other words, you are given a number k and you want to know whether there is an s such that every integer can be written as sum of s kth powers. The whole origin starts with a theorem of Lagrange, who proved that every integer can be written as sum of 4 squares. Therefore, you take any integer, you can always write it as sum of 4 squares, a square plus b square plus c square plus d square. And that is exactly what Waring wanted to know, whether it can be extended for any kth power. And this is a problem in which, as I told you, practically every number theorist in India worked, including Anand Rao. And not only that, on the Teachers' Day, this is what I really want to mention, that he also had some brilliant students. And some of his students include S.S. Pillai, about which we will talk in a little more great detail later, Thirukallabara Vijayaraghavan, and K. Chandrasekaran. This K. Chandrasekaran is the KC whom I mentioned earlier. Now let's talk about T. Vijayaraghavan. Thirukallabara Vijayaraghavan, he worked with Hardy in the years between 1925 and 1928. Again, he started with some summability, which is not too surprising because practically everybody at those days started with the summability. And he later shifted to Diophantine approximation. What is the question of the Diophantine approximation? You may recall that a complex number alpha is called an algebraic number if there exists a polynomial p of x such that the p of x should have integer coefficient and p of alpha should be 0. In other words, alpha is algebraic, means that this alpha is root of a polynomial with the integer coefficients. For example, square root of 2. Square root of 2 is an algebraic number because it is the root of the polynomial x square minus 2 equal to 0. And it is known that the numbers like e or pi are not algebraic numbers, which means that you can never find out a polynomial with the integer coefficients whose root is e, and you can never find out a polynomial with the integer coefficient whose root is pi. And what is the type of question which Vijayaraghavan was interested? The question Vijayaraghavan was interested is, suppose I give you an algebraic number, let's say square root of 2, okay, then how closely this square root of 2 can be approximated by rational numbers? This is an important question in number theory, and Vijayaraghavan had some earlier work on that, etc. But then later it was Axel Thue proved something which was improved by Siegel, and finally the problem was completely settled by Roth, and for which he got the Fields Medal. And then there is another number for which Vijayaraghavan is well known, is the so-called Piso Vijayaraghavan numbers, and this will be slightly difficult for me to explain. Therefore, there are many things which Vijayaraghavan has done, and like things like Piso Vijayaraghavan number, etc., for which he is theoretically very famous. Now let me talk about Yasri Chawla, because about Chawla will come even later. He got his PhD in 1931 under J.E. Littlewood, and probably most of you would have known that Littlewood and Hardy and Littlewood were the people who really supported Ramanujan. And he returned to India in 1936. He was born and brought up in London, I think. But he was returned to India in 1936 to become a professor at Lahore. And he immigrated to USA in 1948. And probably most of you would have guessed why he immigrated to USA in 1948. I mean, he had certain bad experiences during that time of partition. And in fact, I was privileged to be his apartment mate when I was in Princeton in 1979, 80s, and we shared the same apartment. And there are times where I have invited him to come to India many times, and every time he would say, Balu, I would like to come to India, but on the other hand, this turmoil which I had at the time of partition always prevents me from coming back, etc. And I don't think he ever returned to India at all. And he is a very famous number theorist. And he was a teacher of Professor R.P. Baba, about whom we will take a later. And he was a very close friend of Pillai. And Pillai, about Pillai, we will talk later. But other than there are many results of Chawla which are sort of well known. And some of the examples being Bruce Rice's Chawla theorem, Ankeny Austin Chawla congruence, Chawla model theorem, Chawla-Selberg theorem, and so on and so forth. Now let me talk about K. Chandrasekharan. K. Chandrasekharan again was a student of Anand Rao, as we saw earlier. And then at the time when he was in Princeton, he was invited to become the HOD of the Department of Mathematics of the Tata Institute. Oh, Tata Institute I have not written. Second HOD of Department of Mathematics of the Tata Institute. He invited him to the Tata Institute. He came. And okay, let me talk about the mathematics and then I will come back to the other things. He again started with the summability and then shifted to Riemann zeta function. And I have already mentioned about what Riemann zeta function is, but since I want to explain a little more about the results of Chandrasekharan, let me sort of explain what the Riemann zeta function in somewhat detail. Riemann zeta function is a function which is defined by summation 1 over n power s, n equal to 1 to infinity. And s is a complex number. I mean, this is the first hurdle which most of you would have when you start the zeta function. The hurdle being that nowadays it is very common to denote a general complex number by z. Therefore, all your complex analysis book will say that let z be a complex number, x its real part, y its imaginary part, z is equal to x plus iy. But when all these notations for the complex numbers were not well settled, completely settled, at that time, of course, everybody was using their own notation for complex numbers because there was no general thing. It has not been standardized by that time. And the Riemann was using S for a complex number. S for a complex number, sigma for its real part, and T for its imaginary part. He was writing S is equal to sigma plus IT. Therefore, S was a general complex number. And therefore, whenever I say Z, yes, you should think of Z, more or less. The Z is what you are more comfortable with. Therefore, let zeta S equal to summation 1 over n power s, and S is a complex number. And this function is known to be analytic in real part of S bigger than 1. Because when real part of S is bigger than 1, this zeta S is convergent, absolutely convergent. And in real part S, if it is strictly bigger than 1, it is in fact also uniformly convergent in every compact subset of real part of S bigger than 1. Since it's absolutely and uniformly convergent to therefore it depends on analytic function. But that is a function which Euler considered first. But when Euler was considering it as a real function. And once you consider it as a real function, then you have this function to the real part bigger than 1, and then there's nothing else which you can do with that. Whereas what Riemann did was that he proved that it satisfies an analytic continuation, which means that in some sense a zeta function can be defined throughout the complex plane. And also it satisfies a functional equation. That is, if psi s is equal to s into s minus 1 divided by 2, pi power minus s by 2, gamma s by 2, zeta s, then this psi of s equal to psi of 1 minus s. Which means this function psi takes the same value at the point s as well as at the point 1 minus s. The type of question which Casey was interested was whether the functional equation determines the zeta function. Okay. And there are various papers which he wrote. These are all more or less in his Princeton period. And then when he came back to India, and when he took over as the HOD, he got a brilliant student by the name Raghavan Narasimhan. And both Casey and Raghavan Narasimhan have done lot of work on the Riemann zeta function and related areas. And all those works are very important. And one of the most important work is so-called approximate functional equation. Since this is again one of the very important results of Narasimhan and Chandrasekharan, let me explain this. It says that I have the summation 1 over n power s n equal to 1 to infinity. This is convergent to the right of 1. It is not convergent to the left of 1, even though zeta function is defined. Zeta function is defined by a different formula, by different analytic continuation. But this series will not be convergent. But Hardy proved that essentially if you take a series and truncate it, that approximates zeta function, which is something very surprising, because you see the finite partial sums would approximate a function when it is convergent. And when it is not convergent, you cannot really approximate, because this function, the summation 1 over n power s, is not even defined there. Therefore, the zeta function is defined by a different formula. And now what Hardy proved is that even though zeta function is defined by a different formula, the partial sums do approximate the zeta function. And Casey and Raghavan Narasimhan proved similar results for a wild case of Dirichlet series. The reason why I gave these results important is you would have seen how great a mathematician he was. He was a great, very great mathematician. But the point is that when people do remember him, they remember him more as an administrator. He was a very great administrator, and therefore, more than his mathematics, his administrative abilities were great, and in some sense, even eclipsed his mathematics. But on the other hand, his mathematics was fantastic, first rate. And more than that, he was an institute builder. That's the point which I wanted to say. Namely, that the Department of Mathematics of TIFR reached greater heights, went into the level of an international level, competing with the international departments, essentially because of Casey's administrative capabilities and vision and nation building. Then R.P. Bamba. R.P. Bamba is well known his work on Minkowski's conjecture, and these are all the areas called the geometry of numbers. And again, unfortunately, in 5-10 minutes, it's a little difficult to explain. More than that, as I was talking about the Chandrasekhar, he developed a great school on the geometry of numbers in the University of Punjab. Oh, I forgot to write. In the University of Punjab, in Punjab University, he developed a very great school, and Bamba was a student of Chawla. And there is one result of Chawla and Bamba, somewhat an elementary result, one would say, which they proved probably somewhere around 1940s, and a result which has not been improved till today. Therefore, even though the proof which they gave is simple proof, that doesn't mean anything, because only has not been able to get even a complicated proof to prove a result which is better than what Bamba was able to prove. And now let me talk about Ramachandra. Okay. Ramachandra arguably is the best Indian number theorist in the post-independent era. And since I was fortunate enough to be his student, and I knew him rather closely well. It was very difficult for me to decide what to write on Ramchandra, because I know practically all the theorems, which each one is important. And when I want to talk about one theorem, then probably I thought the other theorem is better, and so on and so forth. And therefore, I will talk about one theorem a little later. But in any case, therefore, I decided that probably I would just say what are his great results. His major results includes Kroneker's limit formula. This was his thesis, which was published in Annals, and a problem which was sort of suggested by Siegel, and using which he constructed what is called the ray class field, which was considered one of the great achievements. And Ramchandra units, these Ramchandra units are the units of cyclotomic fields, and this is exponential theorem, and Grimm's conjecture, about which I will say a little more. Then lower bound or the mean value for the Dirichlet series, which is one of the very, very important contribution of Ramchandra, which has been used by many people of proving this, and omega results. And yeah, I will probably say what omega result is a little later, Huxley contour, etc. Let me just explain Grimm's conjecture, because in this offline thing, without really looking at any of your faces, it is a little more easier to explain results which are in combinatorics than in any other area. And this Grimm's conjecture being somewhat of that nature, let me explain what it is. Grimm's conjecture is the following. Let n and h be natural numbers, and then you consider this interval n plus 1, n plus 2, n plus h. Therefore, I take two natural numbers n and h, and then I get an interval of length h starting with n plus 1. What I want to know is whether I can find out primes p1, p2, p3 up to ph. There are h numbers, and I want h primes such that this p1 should divide n plus 1, p2 should divide n plus 2, p3 should divide n plus 3, and ph should divide n plus h. Therefore, p1 divides n plus 1, p2 divides n plus 2, ph divides n plus h. This is not difficult, but in such a way that these pj's are all distinct. Therefore, I should be able to get distinct elements such that every pj divides n plus j. Is it possible to do that? The original conjecture of Grimm was that if all those numbers n plus 1, n plus 2, etc., n plus h are composite, then this has to be true. If all the original numbers are composite, then it has to be true. And what Ramchandra, along with Shore and Tideman, proved is that star is true if your length of the interval is not too big. The length of the interval is only less than constant times log n by log n whole cube, then the star is true. Then in that case, it is possible for you to get primes such that you can associate p1 with n plus 1, p2 with n plus 2, etc. Okay. What is the connection between this and the original conjecture of Grimm? Whether this will prove the original conjecture of Grimm? Unfortunately not, but there are certain conjectures, particularly called Silva's conjectures, on the distribution of prime numbers. And if you assume those conjectures, then Ramachandra's theorem would imply Grimm's conjecture. Therefore, Ramachandra's theorem will not imply Grimm's conjecture unconditionally. In order to prove the Grimm's conjecture unconditionally, you have to take h to be much, much bigger, something like an n power half plus epsilon. But on the other hand, if you assume the conjectures of Selberg on the distribution of primes, then Ramachandra's theorem will imply. Then let me talk about C.P. Ramanujan. Again, many of the people who started with, of course, with an exception of Ramchandra, who dabbled in many aspects of number theory, but I don't think outside number theory he did do anything at all. But most of them again confined themselves to the various things of number theory. And this is the first person who was a great expert in two different, completely different areas, both in algebraic geometry and in number theory. And let me talk about his work on algebraic geometry. But let me say about number theory. His most important work in number theory is again on Walling's problem on number fields. As I told you, the Walling's problem you get again and again. People Ramanujam's work on Walling's problem on number fields is one of the crowning achievements which came from India. But we have talked about many people except for one, and that is Subbaya Shivashankara Narayana Pillai. And apparently, I read somewhere that L Dash has never called him SS Pillai. He was always would refer to him, of course, not call, would refer to him as only Subbaya Shivashankara Narayana Pillai. Okay. And because I about Shivashankara Narayan Pillai is what whom I want to talk about somewhat in a great detail. Subbaya Shivashankara Narayana Pillai was born on 5th April 1901. He did his BA at Trivandrum in Maharaja's College, worked with both Professor Anandarao and Vaidyanath Swami. Vaidyanath Swami also was a great number theorist, but I didn't mention much about him essentially because his works on the other areas, particularly in topology, is much stronger than his work in number theory. And in fact, if I remember that, Vaidyanath Swami was the first person who wrote a book on topology in English. At that time, all the books in topology were only in German or French. Then he joined Annamala University as a lecturer. After some stint in Travancore, he shifted to Calcutta in 1942. Okay. In 1950, he was traveling to USA. And he was traveling to USA to participate in ICM. And I don't know how many of the students know what an ICM is. ICM, International Congress of Mathematicians, which is a conference of mathematicians, which it takes place once in 4 years. And we also had one such one in Hyderabad in 2010. And this is one of the most prestigious conferences to which, of course, Pillai was going. And this is the place where the Fields medalist, which is equivalent of the Nobel Prize, are announced. Okay, 4 Fields medals are announced in the ICM. And he was planning to, after ICM, he was planning to spend 1 year in the Institute of Advanced Studies. The Institute of Advanced Studies is again the Mecca Medina of the mathematicians. Every mathematician want to spend some time there, and that's one place where which is the place which is in recognition of the great work which has done by the mathematicians. Therefore, it would be essentially having in its permanent thing, the institute would be having all people who have done really great work, got Fields medals, and so on and so forth. And then it will invite many youngsters, postdocs, and so on, who would be then able to interact with those Fields medalists and learn. But alas, the flight got into air crash on 31st August 1950, and India lost one of the best mathematicians. And that's exactly we are having this remembrance now, because 31st August, just 4 or 5 days back, and this is his 71st year of remembrance. Okay, Walling's problem. Again, one of the crowning achievements of Pillai is settling the Walling's problem. That's exactly what I was telling earlier. I mean, there are many Indian mathematicians did work. Of course, it was an important problem. Many people worked, including Hardy, Gilwood, Davenport, Vinod Rao, and all great mathematicians worked. And since the great achievement of Pillai is on Walling's problem, let me mention what the Walling's problem is. I have already explained what Walling's problem is, that the number of ways of writing n has a sum of s kth powers Therefore, whether given a k, whether there exists an integer s such that this n can be written as sum of s kth powers. And if such an s exists, what is that minimum? Call that number as little gk, because there is something called a capital Gk, which is in the variance problem, which is slightly different. But we are interested in little gk. And what one was interested in little gk, and nobody had an idea what the little gk would be. And what Pillai managed to prove is that this the little gk is exactly is equal to 2 power k into integral part of 3 by 2 power k minus 2 if 6 is less than or equal to k less than or equal to 100. Therefore, he was able to give an exact value of g of k for between 6 and 100. And when k is bigger than 101, then he said that is exactly this number or probably one more. That's all. It has to be this number or probably one more. And even he gave a criterion when this will be the first number and when it will be the second number. And but only unfortunately it is not, we do not know how to check that criterion. To, I mean, given a k, I can check the criterion, but to say that what are the cases which will for which the criterion would be true and what are the cases for which the criterion would be false, etc., that seems to be difficult, and that seems to be coming in a completely different area of what I was talking about, this approximation of algebraic numbers. But anyway, I mean, of course, that means essentially only a couple of values of k were left, 4, 5, etc. were left. But from 6 onwards, practically, he completely solved the problem and gave an exact value. I mean, okay, almost exact value. The other one for which Pillai was famous is again so-called Differential approximation, which says the following. Suppose A, B, M, and N are natural numbers, and X and Y are also natural numbers. Then, if am power x minus bn power y is not equal to 0, then am power x minus bn power y is bigger than or equal to m power 1 minus delta into x. Therefore, let me just explain what this thing means. This essentially means that suppose you are given an A and a B and an M and a N, and now I want to know whether I can find out an X and Y such that am power X is not equal to Bn power Y, but on the other hand, am power X and Bn power Y should be close to each other. Let me give a simple example called the Catalan's conjecture, which means let's take A is equal to 1 and B is equal to 1. Therefore, you have an m power x minus n power y. And then you want to know whether m is equal to 2, let's say, and n is equal to 3. Therefore, you have a 2 power x minus 3 power y. Therefore, in this case, special case 2 power x minus 3 power y, what I want to know is whether I can choose two integers x and y such that 2 power x and 3 power y will be very close to each other. And Pillai's conjecture is no. 2 power x minus 3 power y cannot be very close to each other. And it will be as big as m power 1 minus delta into x. That's exactly. Okay, therefore, let me again repeat. Let me take A is equal to m equal to b equal to n equal to 1, as A equal to b equal to 1 and m equal to 2 and n equal to 3 as a simple example. Then, therefore, I have a 2 power x minus 3 power y. I don't want 2 power x equal to 3 power y, but I just want to have 2 power x and 3 power y should be very close to each other. Of course, you can give one example immediately, 2 cubed minus 3 square. 2 cubed is 8 and 3 square is 9, and therefore 2 cubed minus 3 square equal to 1. But what we are talking about is for the large enough xy. If x and y are large enough, then whether 2 power x and 3 power y can be close to each other. And the theorem is that this 2 power x minus 3 power y would be bigger than 3 power 1 minus delta into x for any positive delta. Okay. And this Pillai was able to prove. And on the basis of that, he conjectured that if 2 power x and 3 power y cannot be close to each other for large values, which essentially means suppose I want to 2 power x minus 3 power y equal to 32, then or 35, then 2 power x minus 3 power y equal to 35 can have only finitely many solutions. Essentially, because when x and y are large enough, then 2 power x minus 3 power y will exceed 35, cannot be equal to 35. Therefore, it can be only for small values of x. And that is the conjecture he made. The equation A m power x minus b n power y is equal to k has only finitely many solutions for a given k. This conjecture is still open. Okay. Now let me say what he did with the Chawla. Pillai had a correspondence with the Chawla for nearly 20 years. And one of their important results they proved jointly is the following. Okay, I mean, see, those days, there's no email. The letter, if you write, the letter will reach the other person probably after a week, and that other person has to think about the mathematics which you have written in the letter and would respond after a week, and that you will receive after a week. Which means essentially, if you write a letter to somebody discussing some mathematics, you can expect a reply only after a month, and that is not that's not so comfortable, but that's all what they had. Not today's like an email where you write this letter and you get a reply immediately. And not only that, if you really want to talk, then you have like various things like Zoom or Skype and things like that, which was not something which was available those days. Therefore, they would always make it a point to attend all mathematical conferences, because the meeting in the mathematical conferences is more or less the only way the two mathematicians would be able to interact with each other. And with such difficulties, with Pillai in the Annamalai University and Chawla sitting in Lahore, worked together. And Pillai had a correspondence with Chawla, and one of the important things is let phi n be the Euler's function, which probably most of you would have known. That is the number of integers less than or equal to n, which are co-prime to n. And then you want to sum phi n. And when you want to sum phi n, sorry, it should be phi little n, sorry. Phi little n, n not exceeding x, n, which means that you take phi 1, phi 2, phi 3, phi 4, phi 5, phi n, and add all of them. And it is known that that number is close to 3 by pi square times n square, and call the difference to be En. Therefore, the summation phi1 plus phi2 plus etc. up to phi n, you write as 3 by pi square into n square plus the difference En. And this type of things is what is mainly number theorists do, analytic number theorists do. They take an arithmetic function, they take a function and then sum it up and see what is the main term, therefore what is close to that, and then what is the error, and what can we say about the error. And if you results like this En is small, these results are called to the O result. For example, in this particular case, one proves that En is not more than constant times n power 3 by 2. The main term you see is n square, and the n power 3 by 2 is therefore very small compared to n square if n is very sufficiently large. If n is sufficiently large, n power 3 by 2 is very small compared to n square, because it goes down by an n square by an amount which is square root of n, which is very large. And to say therefore this En, this difference is so small, these type of results are called O results. And on the other hand, this En is not always small, somewhere sometimes big. For example, if you say that En would be at least as big as n sometimes. Okay, En will always be less than n power 3 by 2, but you cannot say that En will be less than n always. There are sometimes En is slightly bigger than n. To say that En is slightly bigger than n, that type of results is called a omega result. And for this particular problem, Chawla and Pillai found a method, a omega result, and more than that, the method of the proof, they developed a powerful method to get an omega result. And the method was exactly so powerful that it was remained unbeaten at least for the next 50 years till Montgomery was able to get an improvement over that result. Okay, and there are various other things about Pillai which I have not talked about. Namely, his work of his student L.G. Sate, and that is a great story, probably which you should read, and I will probably give the reference to all those things. That work of Sate, and let me all close with one result of Pillai, again of the combinatorial nature. I mean, which you will be able to appreciate, and then you should probably. I'm not giving the proof, but I'm just explaining what the result is, and then you should try to read the proof from Pillai's work. Okay, what is the result? The result is consider the set of m consecutive integers. Any set of m consecutive integers, n plus 1, n plus 2, etc., n plus m minus 1. If you take m consecutive integers around 1940, there was a conjecture that when you take this product of m consecutive integers, it is never a square. Therefore, if you take product of two or more consecutive integers, it's never a square. If you take two consecutive integers and multiply, it cannot be a square. If you take three more consecutive integers and multiply, it cannot be a square, and so on and so forth. How will you prove that? Okay, the proof is very difficult. I'm not going to give, but on the other hand, at least one special case I know how to do it. This special case which I know how to do it is when this length of interval is bigger than n plus 10. If the length of the interval is bigger than the starting point plus 10, then I know how to do it. How do we do that? The way to do that is we choose k to be n plus m minus 1 by 2. And if you choose k to be n plus m minus 1 by 2, then this k lies in that interval a. That is because m is bigger than n plus 10. Since m is bigger than n plus 10, you can check k is bigger than or equal to n. Since k is bigger than or equal to n, therefore the k will lie in that interval. But once k lies in this interval, then by Bertrand's postulate, there is a prime between k and n plus m minus n. Okay, but probably most of you would have seen what is Bertrand's postulate. Bertrand's postulate says that if you take a number and twice of that number, then between those two, there will be always a prime number. If you take some integer, L, and twice of that number, 2L, and between any L and 2L, there will always be a prime number. And see, it so happens that proving this Bertrand postulate is somewhat much easier than proving the so-called prime number theorem, which says that the number of primes up to n is n over log n. Therefore, for prime number theorem, this Bertrand postulate will easily follow. But on the other hand, the prime number theorem proof is rather very difficult, and Bertrand postulate proof is rather easy. Prime number theorem says that the number of primes up to n is around n over log n, whereas Bertrand postulate says that between n and 2n there will always be a prime. And because of that, there are many people who give nice simple proof for Bertrand's postulate, which includes Chebyshev, which includes Srinivasa Ramanujam, which also include S.S. Pillai. There are many people who gave a very simple proof for Bertrand's postulate. And because of Bertrand postulate, which means between k, l and 2l there will be a prime number, it is very clear the way I have defined k, between k and n plus m minus 1 there will be a prime number. And also very clear that the 2p will be outside that interval, because k is practically n plus m minus 1 by 2, and then your p is bigger than k, and 2p will be bigger than 2k, and therefore the 2p will be bigger than n plus m minus 1. Therefore, p lies in that interval, and 2p does not lie in the interval, which simply means p lies in that interval and 2p lies outside the interval. That means the product n into n plus 1 into etc. n plus m minus 1 has a p in it, and it does not have a p square in it, because there will be only one term containing p, namely p itself. Even 2p will not be there. Since 2p will not be there, there will not be p square. Therefore, once the product has a p in it and not p square, it cannot be a square. As simple as that. In the prime factorization, p p occurs to the first power. If p occurs to the first power in a prime factorization, that number cannot be a square. Now, Pillai wanted to generalize his result. And Pillai wanted to generalize his result, and he thought, what is the idea that is essentially used? The idea which is essentially used is that you are able to produce a prime number, okay, p, but not 2p. In other words, you are able to produce one number which is co-prime to the rest of the elements. Therefore, since this number is co-prime to the rest of the elements, therefore somehow you have been able to manage to prove it. And what Pillai thought was probably if one can somehow prove that there will be one element which is co-prime to the rest of the element, one may be able to do something. And therefore that is the question which he asked. Let A be again the set of m consecutive integers. This is all what you are having. A be a set of m consecutive integers. And we say k in that set is a good number if k is a co-prime to the rest of it. That's exactly what I want. I want to know whether there is one number, a good number, which is co-prime to the rest. If the number is co-prime to the rest, probably one may be able to do something with that to get the complete result. Therefore, the question which Pillai raised is that is it really true that every set of consecutive integers, okay, every set of 5 consecutive integers, every set of 7 consecutive integers, every set of 23 consecutive integers, they all have a good element. Therefore, if I give you a set of concepts of 23 consecutive integers, is it necessarily true that I can find out one element which is co-prime to the rest? Unfortunately, the answer to that question turned out to be negative. Okay, it is not true. And in fact, Pillai himself was able to prove that if m is less than or equal to 16, then a set of m elements has a good element. But for every, okay, that's which means only for up to 16 he was able to prove it. Up to 16, if you have a set of 16 elements, 15 elements, 12 elements, then you can always find out one element which is co-prime to the rest. And unfortunately, it fails from 17 onwards. For every m which is bigger than or equal to 17, there are counterexamples. For example, for m equal to 17, you can try this counterexample 2184 to 2200. Then you can see that there is no element which is co-prime to the rest of you. I urge you to look at that proof. Incidentally, Ella settled the conjecture by a different method. Okay, to whatever I am saying, let me give a reference. One is from article which I wrote, highly composite, which is in the proceeding of the ICM 2010 about which I was talking. And the second is collected work which I edited with Tangadurai or the Shivshankar Narayan Pillai. And if you have this collected work, then you can look at this, his proof and so on and so forth. Again, let me thank the organizers for this opportunity to talk to you on the Teachers' Day. Let me all bless all the young teachers who are doing a noble job of training and enthusing students of mathematics. And let me all again bless all the young students who have been fortunate to have such a good teachers, and I bless that you would excel in whatever that you plan to do in the future. Thank you.
Mathematics may not
Mathematics
teach
may
us
not.
love or subtract hate, but it gives us hope that every problem has a solution. I thank Dr. Balasubramaniam for his wonderful lecture. Now the session is open for question and answer discussion. If anybody have any questions, you can ask. Dr. Vijay Kumar sir?
Yes, madam.
Yes, sir.
Huh.
Is there any questions? Clarify.
Dear viewers, if there is any question, please write it in the comment box, and Sir will answer for that.
Where is the chat box? Oh, here it is.
Yes, sir. On your right.
Yeah, yeah.
Is there any question? Sir, please check the YouTube live chat, sir.
Yes, yes, yes. If if they typed in there, we can receive the question here also.
Yeah.
Okay, sir. Okay, sir. Yes. I think no question, right?
Yeah.
Yeah, there is no. Sir,
Yes,
there is
madam.
no
There is
question.
no question.
Sir,
Hmm.
yeah. Can we
I
move
don't
it
see.
further? Yes, sir. Even
I don't see a question.
Yes, sir. There is
yes,
no
sir. No, there
question
is
from the chat box.
no questions from audience, sir. Sivaraman, sir.
Sir, thanks very much for your enlightening talk, sir. We were
Welcome.
actually taken uh, to the memories of great Indian mathematicians, and we feel very humbled to hear from you.
Okay,
Yes.
let me put this off.
I'm sure most of the young students could have been benefited from this.
Yes. I mean,
In fact, I
Okay.
wrote a
it's
Tamil
not
book
very clear. It was
about
not very
Indian
clear to me which
mathematicians. I
level
would like
to
to
pitch.
send a copy to you.
So,
இந்திய கணித மேதைகள் அப்படிங்கிற ஒரு தமிழ் புஸ்தகத்தை எழுதியிருக்கேன் சார் நான்.
அப்படியா?
So maybe I can. ஆமா ஆமா.
Oh,
அதில்
oh,
வந்து I
okay.
have written about 32 mathematicians, Indian mathematicians.
Okay. Okay. Just hold it.
Yes, sir. Sir, shall I
Can I
continue?
talk to you a little later?
Okay, madam. There
Okay.
are no questions. You can
Okay.
propose
Yeah.
call
Yes.
vote up or vote up next.
Yeah. I would like to admit my thought. A good event never ends in the world. They take a pause, keep us waiting for the next. Now I call Dr. Yokesh, trustee of Pi Mathematics Association, to deliver out of thanks.
So, very good afternoon to every one of you. It's a great privilege to give the vote of thanks for this wonderful session. So, first, it's my duty to thank our guest, Dr. Balasubramanian sir, for his wonderful lecture, which enlightens the young research scholars to know about the great Indian mathematicians and their contributions in various fields. So especially today we learn know about the great Indian mathematicians, starting from Anand Rao, S.S. Pillai sir, Vijay Raghavan. Really, we are so happy that to know about Vijay Raghavan sir. He's working along with the great mathematician Hardy and Chandrasekhan sir, Chawla sir, and Ram Prakash Bamha and Ramachandran sir. So really, so it's a great honor to know about the great Indian mathematicians and their contributions in various fields, especially they are working for Riemann zeta functions that you sir explained very clearly, and a lot of conjectures are hosted by the Indian mathematicians, and still the research is going under this field. I think this will motivate our young research students, those who participate for this event. They can take on such conjecture and can work on this problem with the guidance of the great Indian mathematicians. So, and I like to share about our Pi mathematics. So yeah, it's a novel and non-profitable NGO and registered charitable trust, and took it as a great challenge to propagate the beauty of mathematics and to disperse the math phobia prevailing among the students. And this is a unique association functioning solely for the purpose of spreading mathematics through uh, publishing books in English as well as Tamil. So far we have totally published nearly 15 books in both Tamil as well as English. We are organizing so many workshops and exhibition for the students to know about the mathematical concepts, and they can get the idea more about how this mathematics to be applied in the various fields. So. So with that, really very thankful once again. Thanks once again, sir, for your wonderful sessions. And really, it is very useful for all of us, and we are all blessed to have a great lecture, to listen to a great lecture from you, sir. And I hope that we are all enjoyed and learn more about the Indian great mathematicians. So thank you so much for thank you, sir.
Thank you. Thank you.
Thank you, sir.
So I
Once more,
special
I thank
thanks
you
to
all
our.
for your attention. Thank you.
So we give a special thanks to our uh, founders, Dr. Shivaraman sir, for organizing such a great events. Really, it's motivating all of us to do something, do contributions in the development of mathematics. We especially thanks our one of the trustee Vijay Kumar sir for his enormous support in organizing such events. A special thanks to ma'am Nisha ma'am for his wonderful. So thanks to all of us. Thank you so much. Thank you, ma'am.
Thank you, sir. Thank you for your great attention. Thank you all.
Thank you.